Hi everyone, in this video we're going to see two applications of the determinant in the context of lines in the Cartesian plane. So we're going to talk about determining collinearity of points in the plane, and then we'll see how we can use kind of the same ideas to find the equation of a line determined by 2 points. All of this is based on a kind of simple idea, and it's one that we're already familiar with when we talked about polynomial interpolation. So we know that the equation of a line can be written as an ax plus by plus c equals 0. We could also solve that for y in terms of x and get a y equals mx plus b kind of equation, but let's stick with this for now. The way that we're going to approach this is by imagining that we're given 3 points and asking, are these collinear? Do we have a situation that looks like all 3 of these points are on the same line? Or are we in a situation like this, where these points don't lie on a line? There's no line I can draw through these 3 points. These are the only lines that are determined by this set of points. So the answer to are all these points on the same line? Yes, looks like this, and no, looks like this. So in a situation where the answer is yes, that means that there's a value for each of a, b, and c, so that plugging in these points into that equation will result in a true statement. In this case, it means there is no set of 3 values, a, b, and c, except 0, 0, 0, that are going to be able to make this equation true for these 3 different points. So let's see an example of how this is going to work. Let's say we're given these 3 points. And from what we just said, we know if they're collinear, there should be a, b, and c, so that when we plug into an equation like this, will give us 0. So let's see, that would say a times 2 plus b times 3 plus c times 1, if you like, is equal to 0. This would say a times 1 plus b times 2 plus c is equal to 0. And this one would say a times minus 1 plus b times minus 2 plus c is equal to 0. Now that looks like a linear system of equations, and I can write out the coefficient matrix like this, and I can write down the entire equation by adding my vector of unknowns and my right-hand sides. This is what we call a homogeneous system. And homogeneous systems always have a solution, right? They always have the trivial solution. In other words, a equals b equals c equals 0 is a solution. But it's not an interesting one, because it's not giving us the equation of a line. It's giving us just the obviously true statement that 0 equals 0. So a homogeneous system has only the 0 solution like this, exactly when this matrix is invertible. So we want to ask this question, are these points collinear in the plane? And if A has an inverse, then the answer is no, because the only way we can make our equation true is by having A, B, and C equal to 0. So what we're interested in knowing is whether or not the inverse exists, and we can determine that by just computing the determinant. Because if the determinant of A is not equal to 0, then A inverse exists. If the determinant of A is equal to 0, then that inverse doesn't exist, and since a homogeneous system has at least one solution, we know that in that case it's going to have infinitely many solutions. So let's check to see whether or not the determinant of A is non-zero. And we know how we're going to compute this, right? We're going to write down this matrix with its first 2 columns copied next to it. And when we do that and start computing the determinant, we'll get 2 times 2 times 1 plus 3 times 1 times minus 1 plus 1 times negative 2 minus, and then we do the backwards diagonals, 1 times 2 times minus 1, and then 2 times 1 times minus 2, finally 3 times 1 times 1. And adding this all up, we get 2. So since 2 is not equal to 0, these points are not collinear. Based on the same idea, we can find the equation of a line determined by 2 points by computing a determinant. So let's see how that's going to work. Again, remember this basic idea underlying all of this is that this is what the equation of a line looks like, and points that are on the same line, when plugged into this equation, are going to give a true statement for the same values of a, b, and c. So let's say we want to find the equation of the line determined by 2, 3, and -1, -2. We know that we should have an a, b, and c value that is going to make this equation true for those 2 points. All right, so we need those 3 values. And we want to get the actual equation for this line. So we can think about setting up, again, a linear system, just like we did with polynomial interpolation. This time our right-hand side is zeros. And we want to be able to plug in 2, 3, and -1, -2. But we want an equation, so we're going to leave this first point as undetermined. To get a non-trivial a, b, and c to be the coefficients in this expression, we need to make sure that this determinant is equal to 0. We need to make sure that the determinant of this matrix is equal to 0. So that's what we're going to do. We're going to set the determinant of x, y, 1, 2, 3, 1, -1, -2, 1 equal to 0. And that'll give us an expression with x's and y's in it. If we rearrange that expression so that we have y in terms of x, then we'll have the equation of our line. So to compute that determinant, I can copy the first 2 columns over here again, and then I know I'm going to go forwards and then backwards and get my expression. So simplifying the right-hand side, I'm going to get, and then solving for y in terms of x is going to give me 5/3 x minus 1/3. And that is the answer I was looking for. So a is 5/3, b would be -1 if I pushed these all to the right-hand side, and c is -1/3. And always remember that you can check by plugging in your points. So if I plug in x equal to 2, what do I get? Well, I get 3. And if I plug in x equal to -1, I will get -2. So that's it for now. Next up is to find areas and volumes by using determinants of 2x2 and 3x3 matrices.